Okay, here we go. This is not fun. That should be what I say the first day. But I probably did. Let's be real. This isn't really math. Okay. I am not going to stand here long enough on every slide for you to write every word, or we won't even get done with a single problem today. The video will be posted. I know yesterday's wasn't. Maybe it was. I don't remember. You're welcome. Okay, here we go. We're going to balance oxidation and reduction reactions. Oxidation and reduction reactions are kind of ugly and kind of really hard to balance. So there's a ton of information about to come at you. So when you balance an oxidation reduction equation, it involves treating on paper only. I love how they emphasize that. The oxidation and reduction as two separate processes. All right, balance these half reactions and then combining them to attain the balanced equation for the overall reaction. So we're going to say like AB plus CD goes to AD plus BC, whatever. Does that all work sort of? Okay, don't worry about the order. But what we're saying now is you're like, all right, we're going to balance what A does and it goes to AD, and like what C does and it goes to BC. And then you balance these and then you combine them. It's a terrible example, but that's kind of what we're talking about. We split it into two parts, we balance each and combine it and cancel out like stuff. It's actually super not that fun, but at the end, if you get it right, you feel amazing. The problem is you don't usually get it right. All right, so we're just going to blow through this and we'll see how it goes. So you assign oxidation numbers to determine what is oxidized and what is reduced. All right, so just determine what's reduced and what's oxidized. And then write the oxidation and reduction half reactions. So if we, in just an example, again, we have Na plus Cl2 goes to NaCl. And we would never, ever, ever do this process to balance that reaction because we can do that in our head. The other reactions are harder. But you would say, okay, this went from a 0 to a +1. So it lost electron, right? So it's oxidized. Then you'd say here, you'd say it's gained. So you would then, you'd say, okay, Na goes to Na plus, and you would balance that reaction. But that's why I said we would never do this because that's nothing, right? But then we'd say, okay, we had Cl2 goes to Cl minus, so you balance that reaction. You with me so far? Yeah. All right. And so then you would make sure that the charges worked. And if you look in one, there's only a +1, but this one has a -2. So we would have to double this whole reaction to make sure the charges equal each other. Sort of with me? So we'd say really, well, it's got to be a 2 if we distribute that. And then we would combine it. So we would say 2 Na. So all of this combines into this piece. That's just ugly. We'd say 2 Na plus 1 Cl2 goes to 2 NaCl. And we'd have it balanced. Now, once again, don't do that. That'd be so stupid to balance it that way with something that's easy. But this is just the idea. We break it into its parts. We do some stuff. We make sure the charges equal each other, and then we combine it all. It's going to get more complicated. All right. So to balance each half reaction, we balance first elements other than H and O. We balance O, next, by adding water. So like if, just an example, if I had like 2 O's here or something, but I had no O's over here, I'd say 2 H2O. Because when we have these happen, they're going to happen in solution. So there's plenty of water around that the reaction can use. There's going to be plenty of H plus and OH minus as well. All right, so to take care of oxygen, excuse me, we add water. Then balance H by adding H plus. All right, then balance the charge by adding electrons. Multiply the half reactions by integers so that the charges gained and lost are the same. So this is what we're going to do. Let me shut the door. Goddard's bugging me. All right, let me see if we have an example next. I have no idea what that is. Oh, I know what that's saying. I don't know what this is saying. This is taking advantage of the fact we're going to say that this is what we follow when it's in an acidic solution. There's another one where it's basic and we use water or hydroxide. Okay, let me find an example here. Oh, I'm not done yet. That's why we're not doing an example yet. Then we add the half reaction, subtracting things that appear on both sides. Make sure the equation is balanced according to mass. Make sure the equation is balanced according to charge. So these are just checks. Like you should be done, but this is where you just double check to see if you did everything right. I'm a little nervous because I haven't done this in 2 years. We'll do it together. All right, they're not that bad, but I'm sure hoping on the slides I have all the instructions again. Oh, sweet, I don't. All right, this is just saying right here, I'll unerase it, but this is an elevated -2, like it's the charge. Okay, so consider the reaction between manganate and oxalate. So we have MnO4 minus, all these are their charges up here, 2 minus, +2 or 2 plus. And really the difference between a +2 and a 2 plus, that's its charge, that's its oxidation number, but they're kind of the same. Like it doesn't, you'll never get it wrong if you put one the other place. Okay, and then carbon dioxide. So whatever, that's just that. Okay, so you took a picture of the steps. The first thing said to balance anything besides hydrogen or oxygen, right? So manganate, or sorry, manganese, I look at that, it's a 1 and it's a 1. So that's taken care of. You with me? The only other thing is C. There are 2 of them here and 1 of them over there. So I'm going to have to put a 2. Oh, I didn't do the whole thing. I'm an idiot. I'm an idiot. I'm an idiot. I haven't broken them down yet. I have to first split them into their 2 halves. And hopefully that's on the next slide already. Okay. So first we have to assign their oxidation numbers. What, Kayla? What is what? Oh, this thing? Yeah, sorry. That's how my computer interprets their arrow sign. Oh. Sorry. It does that all year, but I guess I've been pretty good and deleted them by now, but not this one. Okay, sorry. Now it looks, she was like, huh? And then her head just kept on going. Yeah, just say, just take my money. All right. Okay, so here is where I first write the charges. I apologize. That's the first step. Assign charges so I can see which is oxidized and which is reduced. So can you explain to your partner why manganese is a +7 for hexanes? How does that work out? How did they figure that out? Oh, hold on, hold on. I'll let you answer after they talk. I thought you were asking a different question.
Oh wait, oh, that's awesome. Yeah,
all right.
Always -2. And so negative is the highest means of the manganese. Got it. And just barely not positive. Wait, why is the O2 plus 4 though? Why can't the C be minus 4? And CO2.
Oh, it's definitely pointing at the wrong spot. Hey, this arrow is off right here. Thank you. That was pointing at the wrong thing. Sorry about that. That definitely should be pointing to the C, not the O. And let me, like, I don't even make these, and they usually don't make mistakes. Huh. Okay, so I must have added that because I'm like, the book never makes a mistake that big. Okay. So here we go. John, you were going to tell me?
So since one oxygen has a right side, that's the charge of the whole.
Perfect. So that's where that came from. Everyone okay with that? We did it a long time ago. We sorted it yesterday. Same idea here. This needs to be a positive 6, but there's 2 of them. So we divided the 6 in half to get the 3. This one's a plus 2 because it told me it was. And then carbon's a plus 4 because negative 2 times 2. And we know it equals 0 unless it has a charge. So we're all set there. Good. Okay. Since manganese goes from +7 to positive 2, it's reduced. I know it doesn't seem like it, but it became more negative. That's how I always, like, it got closer to a negative value. So it's reduced. Next, since carbon goes from +3 to +4, it is the one that's oxidized. It's right here. We had 2, so negative 2 times 4 was negative 8. And then, so this really has to be 6 because it equals negative 2. All right, but then you take 6 and divide it in half because there's 2 C's.
I was in the counting for that.
Yep, you're good. Okay, hopefully it's put together on the next slide. Yeah, perfect. So here we go. Oxidation half reaction. So we took C2O4 2 minus. That's its charge. I don't love how weird that looks. And then we first balance it. That's what I did before. We balance the not hydrogen or oxygen atoms. So since you had 2 carbons, we had to double that. Easy enough. So we put a 2 in front of CO2. That's your first step. Balance anything besides H and O's. Next. All right. The balance, or we're still right here. It's kind of weird how I did this, I guess. The oxygen is now balanced as well. So if you look at the oxygens, you had 4, but when you doubled CO2, you now have 4. Okay, now before this wasn't here, right? That was not there before. So it says the next thing is we would balance the charges. So if it's negative 2 on one side, then we would say over here, it must have 2 electrons. The charges have to equal 0 in each half reaction. So sort of weird. I definitely am aware of that.
Is there any way to stop making a reaction?
Making the half reactions.
Well, like, is there any way to get C2O4 and then just take out the electrons without adding it to anything?
No, like, sure, you could turn it into plasma, but besides that, no.
You're adding 2 electrons to make it so that they both have a negative 2 charge.
You want both sides to be equal, because the 2 electrons, if there's no more negative charge here, then they had to go out somewhere. Yeah.
So they're not, the 2 electrons aren't attached to the surface, they're just kind of like floating around.
They're out there. They're gone. And they're not really out there. They went somewhere. But right now we're on the oxidation. And remember how it said we only treat it on paper, like it's a half process? Because we're only doing it on paper. These didn't just poof, go into the nether. They went to the other thing. They went to the thing that was reduced. Which I don't remember what was reduced. Carbon? No. Manganese. So manganese took them.
But when it's doing the half reaction paper, you put it with the.
You put it on the other side of wherever the negative was, which is the thing that was oxide. Okay, yep. All right, now next. This is balanced. It's balanced by mass and it's balanced by charge. So that's just half. That's the oxidation reaction. Next, I'll just leave it. Do I want to leave it? No, I don't. We'll get rid of it. So the next thing we do is we have the manganate and the manganese. We have to balance those. So the first step here is to balance the non-oxygen or hydrogen. All right, you can see here the manganese is balanced. There's one Mn, one Mn. But oxygen is not. That's your next step down, then it would be hydrogen after that. So oxygen is not balanced. I have 4 oxygens here, correct? So how many do I need on the right side? I need 4. So since this is in a solution of water, I can say that 4 waters were used up in this reaction. That's fair. It's like us breathing. We don't really put air into the equation, but we can use it whenever we need it. We got oxygen in there. We just take it and we use it and we're good. Okay, now that made something else out of balance. Go ahead, Reese.
How many more units do you have?
This is it. We have like 2 total days left. And then it's review. All right. So now the next step is to balance the hydrogens, right? Oh, I didn't put, we needed 4, right? Sorry, 4 waters to get the 1, 2, 3, 4, 1, 2, 3, 4. You with me?
Yeah.
Okay, so I balanced oxygens with water. Now I got a, not a mistake, but I got to fix the H's. How many H's are there?
There would be 8.
There's 8, so I add 8 H plus. Now, that's fair, because remember I kind of rewound a little bit ago and said, oh, I got to remind you, this is in an acidic solution. That means there's plenty of H plus around that we can use if the reaction needs it, it can find it wherever it needs it. All right, I kind of went out of order. The next slides will just talk us through this piece. So yada, yada, yada. I wonder why I changed colors, but I did. Okay, now we balanced the hydrogen. We added the 8 H pluses to the left. Good so far? Okay, then we have to balance the charge. All right, so this is the answer down here. If you look over here, we had we had 8 pluses. You good with that number? And then we also had a -1. So we had a +7 right here. Everyone see where I got that number? I know it's weird. And then over here, my total charge is just a +2. They have to be equal. So I add 5 electrons. Why am I adding it on the left? Anyone know? What, and it's kind of what some people mumble. If it's reduced, look at the screen for a minute, look at me for a minute. If it's reduced, it's gaining, right? So these are the things that are gaining, these are the things that came out. So manganese takes these. Be fair, are we all right with that? All right, so we have 5 negatives, right? And then I don't know where to put them, but we have 5 here. We had 7, or sorry, there we go. That makes more sense. And now it equals a +2, which is what we need.
Are we gonna do
We
that?
need, hold on. Yeah, not probably today because we're on like a super short schedule. In the oxidation reaction, where were the electrons? They were over here, right? Make sure they're on opposite sides, because one gains and one loses. They have to be on opposite sides. The electrons came from the loser, which was carbon, and they go to the gainer, which was manganese.
The reduction reactions always have electrons on the left side.
When you do that half reaction, yeah. Because when you get done overall, they're not going to be anywhere. All right, so here we go. Now we evaluate the two half reactions. So I've just copied down what we had before. We had our carbon or our oxidation. We know this is oxidation because it lost. The things that come out of a reaction are the things that are lost. So there's your electrons there. This is my reduction. I know that they're gained. Things that are gained are on the left. Okay. Now, this part, a ton of kids skip, and it's kind of sad because you get so far, and then in the end, it doesn't even matter. Everyone's welcome. Okay, these have to equal. So how can mathematically a 5 and a 2 ever be the same number? You times them by each other. So everything in this top row must be multiplied by 5. Ugh. Everything in this bottom row must be multiplied by 2. Every single thing you see there. Okay. So 5 of those, 10 of those, 10 of those. I think everyone else thought it was worse. All right. 10 of those. Wait a minute. 10 of those? Well, that was the whole point, right? How many of those? 16, 2, 2, 8. Hey, what can I cancel out just to save me some time? The electrons cancel out. That was the whole point of this activity. So now, hopefully I just have it typed on the next slide because I don't feel like rewriting that. Please, Tom. To tell if you did it right. No. Because the electrons, you had to balance the oxygens, which made you have to have hydrogens, which then you can find the electrons. It all depends on every step. We can't skip any of them. Okay, now here's your answer. Here's your answer. All right, we should eliminate these.
Oh.
Yeah, that's what we got. Okay. If they,
I'm just saying it seems like it's easiest just to look at the electrons.
but the electrons didn't exist in the original problem. Like you don't just see them.
Oh, yeah, we actually had to find
We had to
yeah.
find them.
Oh my gosh.
Okay, so this is your real answer. You should eliminate the electrons. Look at the screen. Sometimes, you remember the first one, we didn't have to balance O or H? In some problems, pretend there was like plus 4 H2O over here. You would combine, you'd have 4 on one side, 8 on the other, so you'd just make that a 4. You with me? Okay. This is how it's asked on the AP test. These are usually multiple choice questions that I strongly feel are a waste of your time. I said that yesterday, right?
Yes.
They will be like this. It will give you the original thing. It'll be A, B, C, D. And then it will ask, what is the coefficient of water in this reaction? It'll be like 2, 10, 15, 8. That's all. It won't ask you to balance it. It will ask for one of the coefficients. It is my opinion that you have just as high odds guessing the answer as doing it. That's a lot of steps. If it's in the multiple choice, don't go low, don't go super high, go in the middle and move on. That's 10 seconds instead of, I don't know, we just spent 8 or 9 minutes on that. There's a million of them. ACT.org or AP.org, or just search AP chemistry tests. They're all over. the videos that you are supposed to be watching on AP Classroom, those have practice questions too.
Oh, I watched last night.
All right, so I guess I did cross it out. This is the real answer right here. Whatever, it's right there. 16H plus 2MnO4 plus 5C2O42, 2Mn plus 2 plus 8 water plus 10CO2. These are not possible to just look at and balance because water and H plus aren't in the written equation. It's just not a thing. And the electrons, yeah, you can do them just based on electrons, except for the electrons aren't listed either. Okay, here we go. Woo. Oh, I wasn't picking on you. I was just saying like, it's just not possible to do it quick. Okay, what time are we out of here?
I have no idea.
That's all right.
Look at it, wait, I don't know. We're out at 1:30.
Okay, so take a picture of that, or you can write it. You have 5 minutes, you can write that, but there's no way we can do the problem in that amount of time. I look good?
Yeah.
I still have my mask tan lines.
My guess is there will be.
You are very
Like, I have to
fine.
take one, you know. Actually, wasn't here, no, go one more day.
Is it bad still?
No, I didn't see a tan line, but you
Oh.
are tan.
I get tan fast.
Okay.
You're whistling.
Oh man, I've never looked better in my life.
I think I'm gonna keep our You're whistling. Cooper, you whistle? Did you whistle that? Oh, no, in my video I did, but I didn't. Oh.
You could hear him whistling.
One girl just kept clucking like a chicken. That
What?
was her whole thing. Braylee.
Who?
That was her whole thing. She just clucked. Like, I can speak chicken. How was real girl? I was like, you guys were different. Like, how were all the videos that you go to? Ours were cringe.
I was only there for the first 3 and then I had to leave.
Cooper hates a life dish. That was the highlight.
Are you serious?
Sophie Burger outside the market.
Are you serious? No, I wasn't.
These kids.
Don't show up. No,
That's terrible.
David said, do you think
That's
there's
so sad.
have like
You could.
actually a chance?
Is your dad a doctor? Uh-oh. Are you related to Dr. Lloyd? I'm sure. Okay, please be quiet. What would your first step be? Splitting it in half. You got to get the half reactions. What would your next step be? No. Balancing it by choosing what first? The not O or H. So you got to balance the chlorine, right? I guess I have 2 minutes and 10 seconds. So we got a +1 -2. So that makes chlorine a what? +1. That's weird, right? But oxygen can make weird things happen. +2 -2, 0. +5 -2. Right? Oh my gosh. Then I go to the half reactions. So what changed? Cl went from a +1 to a 0. That became more negative. So it was reduced. And N became oxidized. So I usually do oxidation first. So NO goes to NO3 -1. That's just me. You don't have to. It doesn't matter at all. Okay, so every time I do these, I do the same thing. I start on the left, but I got to add so much stuff in the middle. Because that's an element. And anything in its pure form is always a 0 charge. Okay, what would be, we'll run out of time, but what would the next step be?
Oh.
Balancing the O's. Right, now balancing the H. So I have to add 6H plus. All right, now this is the oxidation. The total charge over here is neutral, right? The total charge over here is +5. I have to add over here, right? You good with that? Why is it on the right? Because it lost. Because it lost. All right, you're welcome.